good afternoon. Welcome to Introduction to Modular Development. I'm Mark, this is Alan. Just a brief word. Alan's going to do most of the presentation, and then we should have plenty of time for Q&A. But I want to make clear that this is the first time we've really come out and done full-length sessions on the module proposal. So we really value your questions and feedback. Please don't be shy when we get to it, because we want to get this right. We don't want to make the wrong thing into the foundation of the platform. So, Alan.
Okay. This, by the way, is very much an intro talk. We've pitched it very much as a gentle introduction to modules based on where the JSR, the current design, and the current EA builds are. So much of what we're going to go through today is the same material you'll see if you start working through the state of the module system document, or it overlaps a little bit with what Mark touched on in the keynote this morning as well. Just the modularity landscape. If you were at the Prepare for JDK 9 talk, I had the same slide here, but I just want to repeat it here for those that may not have seen this. The JSR that is defining the module system is JSR 376. That's the JSR that Mark is leading, started earlier on this year. That is what is defining the module system for the Java platform. That is still work in progress, and everything that we're actually doing to implement the reference implementation of that can essentially be considered prototype design until that design is further along. There's another JSR that will need to be submitted for Java SE 9. That's the one that will be the JSR that is the umbrella JSR for the platform. So that'll cover all the major features and everything else going into JDK 9 beyond the module system. We're doing the implementation, and particularly the reference implementation for the module system in OpenJDK is part of Project Jigsaw. Project Jigsaw has been running for quite some time. There was various iterations of prototypes and prototype designs going back a few years. And it's now currently at the point where it's synchronized with the current design that's on that has been proposed. There's a bunch of JEPs or JDK enhancement proposals that are being done as part of the implementation. Some of these are already in 9 because they're mostly about preparing the platform for 9. JEP 200, which I mentioned earlier on, is the modularization of the JDK. That's where you'll find the module graph. JEP 201 is where is the effort to reorganize the JDK source code as modules and the JDK build to build it as modules. So this has all been done in JDK 9 already. JEP 220, which I spent a little bit of time on in the Prepare for JDK 9 talk earlier on, is all about changing the output of the build, what the runtime structure is. This is all preparing the platform so that we can actually link in not just JDK and standard modules into the runtime. We can link in other modules, and we'll have one or two little examples today, and then more tomorrow in some of the other talks. JEP 260 is about encapsulating the non-critical APIs. That's what a lot of today's earlier talk was about. And JEP 261 is the JEP that is the implementation of the module system. That augments what's being done in the JSR. And is actually well worth a read. And by the way, all of these, it might look like there's a lot of bureaucracy here with all these numbers. These are living documents. They're quite useful as reference material to be able to, especially when they're kept up to date, to see all the detail as to what's going on in JDK 9 and all these different efforts and JEPs. So 261 has a whole bunch of details. I'll touch on some of the command lines changes to the compiler, to the Java launcher today. There's a lot more detail that you'll actually find in JEP 261. So this is the second of 4 talks that we're doing at Devoxx. The other 2 talks are that we're doing tomorrow, or the advanced talk first thing in the morning, and then the under the hood, which is the advanced talk tomorrow evening. So I'll give reminders and pointers to those later in the slides. So this, as I said, is a real gentle introduction. So we're going to start right at the beginning with what is a module. and then we're going to slowly build up the concepts for about for a number of slides, and then I'm going to bring you through some of the command lines for compiling modules, for running with modules. So this is all really basic stuff, and tomorrow then we'll build on that with some of the advanced slides and migration with real examples. One other thing about the intro slide is we're just using very, very simple module names for now. They're not real module names. Tomorrow's example will be using real libraries, which we'll actually show how we migrate those libraries to modules. And this is done deliberately this way, so that it's intro first, get the concepts on the table, and then tomorrow we go through the more advanced topics. So starting with a module, what is a module? Well, a module we like to think of as a self-describing collection of code and data. The most important thing about this slide and for the beginning of this talk is modules have names. In this slide, the module is called conf_foo_bar, and we'll build up on this over the next couple of slides. So the code that is in a module, if a module has code, and if it's Java code, then it's organized as packages. In this module, we've got 4 types that I'm showing you here. Then they're organized into 2 packages, conf_foo_bar alpha and conf_foo_bar beta. In addition to into Java code or Java classes, modules might have native code, they may have resources, they may have other configuration. I'm not going to go through all of those as part of the intro. For now, we'll just think of code as modules as having code, and they're all organized by package. The module description is expressed in a module declaration. The module declaration is in a source file named javainfo.java. By convention, the module info.java is placed in the top level directory, the top of the source directory. So in this example, we've got 4 types. The source files for those 4 types are organized by package. We've put the module.info in the top level directory of the module. What's in the moduleinfo.java source file is module keyword and then some curly brackets, and we'll build up what's inside that in the next couple of slides. So it's module name, and then we'll get into what is in the module declaration in the next couple of slides. So this is a very basic start. Within the module declaration, we may have a number of requires clauses, and this is how one module expresses a dependency on another module, and that dependency is expressed with the module name. In this little naughty example, we have conf_foo_bar that has a dependency on conf_foo_baz. We'll assume in this example that conf_foo_baz is a library. So we express that dependency with the requires clause, and this is going to be important at both compile time and at runtime. I'm going to start building up this example over the next few slides. So we're now going to introduce a 3rd module into this, which is conf_foo_app. This, in our example, is going to be our main application. And it has a dependency on 2 modules, conf_foo_bar and java.sql. So there's a require clause for both of those modules. So this is a very, very simple dependency. Java SQL, you might wonder what that's about. For now, just think about it as the module that has the JDBC or the Java SQL API. So now we're going to start building up a module graph. So I've shown here the 3 conf_foo modules that I have. conf_foo_app depends on conf_foo_bar. conf_foo_bar depends on conf_foo_baz. And we know we've had Java SQL on the last slide. We have it here as well. For this slide, I'm bringing in another module into the graph, which is Java Base. Java Base is the core of the Java system. That is where Java Lang Object lives. It's where all of the core APIs live. Every module depends on Java Base, whether it expresses that dependency or not. It's like every class ultimately depends on Java Lang Object, whether its source expresses that or not. So Java Base is the core of the system. So I'm going to expand out the graph a little bit more and show what Java.SQL depends on. So what we're going to do is we're going to resolve the top level module here, confu app, and then we're going to build up the module graph by resolving it, confu app, and then all of its dependencies. And the result of this is the transitive closure computation and this module graph that I have here. Java SQL, which I had in the last slide, has dependencies on other modules, Java XML and Java logging. These might not be obvious dependencies unless you know the JDBC API in detail. There are XML types in the JDBC API, so that is why that dependency is there. As I said in the last slide, every module has a dependency on Java base, so therefore we see an edge in this graph from every module to Java base. When a module depends on another module, we say that it reads that module. So in this example, confu app depends on and reads the Java SQL module. The Java SQL module has a dependency on the Java XML module and therefore reads that module, and so on. And the readability is something that we'll build up over the next number of slides. If you're used to Maven or used to any other build systems, what you have here is essentially a dependency graph. And what I want to do over the next couple of slides is transform this into a slightly more enhanced readability graph, because readability relationships in the module system are really the basis for the reliable configuration that Mark talked about in the keynote this morning. So in order to expand this a little bit, I'm just going to take a subset of this graph and with three modules. Our confu app, which depends on Java SQL, which depends in turn on Java logging. So I just want to concentrate on these three modules for a few minutes. And I'm going to start showing a little bit of code as to what we might see in two of these modules. So what we might have in the Java SQL, in the confu app module, is we may have some code that's using some of the types in Java SQL. So if you read a module, then you can make use of the types in that module. So confu app reads the Java SQL module and is making use of types in that module. The type in this example is Java SQL driver, which I assume most people will recognize. Within the Java SQL module, we have the driver class. And one of the public methods in the driver class is a method that returns a logger. There's a method in Java SQL driver called getParentLogger that returns something called logger, which is of type Java util logging that you will see in the Java logging module. So the logging is in Java logging, and something in the driver class in the Java SQL module has an API that returns a logger. Now let's go back up to the confu app and we look at the code that we have there. It has a reference to a Java SQL driver. It's calling getParentLogger, and then it's calling a log method on that. So what this means is that somehow confu app is making use of a type in a module that it doesn't read. So how do we address that? One way we could do this is you could actually change confu app to have a requires on the Java logging module. That will work, but it's a little bit inconvenient for those using the driver API. Using anything in Java SQL, the applications would need to remember to have a requires on Java logging. And in the last code example where I'm chaining some of the method invocations, it's not obvious that I have a dependency on this other module. So the way the module system can help with this is using this notion of implied readability. In the module declaration for Java SQL, it not just requires Java logging, it requires public Java logging. What this means is that anyone that reads or depends on the Java SQL module will now also depend on and read the Java logging module. This is implied readability. So this yellow edge that I have on the slide, if we start adding these implied readability edges to our module graph that we had a couple of slides ago, we end up with this. This is our readability graph. There's the Java SQL module does a requires public on Java XML. It does a requires public on Java logging. Therefore, anyone that reads the Java SQL module also reads the Java XML and Java logging module. So what we have on this slide is our readability graph. So that's requires and readability. I now want to introduce the other part of the solution, which is encapsulation. So I want to introduce now the exports. So in addition to having requires clauses, a module can also declare the API packages that it exports. In our confu bar module, we have it exporting 2 packages, confu bar alpha, confu bar beta. Any of the other packages that are in that module are not exported. They're not going to be accessible to anything outside of that module. Essentially what we can do with modules is we can split a library or a module into 2 parts. The part that is exported, these are my exported packages, and my internal part that is not exported. Once we combine exports with the readability from the previous slide, we can start to reason a bit about accessibility. Our confu app reads confu bar. That allows it to access the public types in the packages exported by confu bar. It cannot access any of the types in the non-exported packages. This includes public types. So there's a pair that you have to get into your head. You've got to read the module, and the module has to export the packages. Once you've got that readability and you have the exports, that allows you to access then the public types in those exported packages. If confu app did not read the confu bar module, then no types whatsoever in confu bar are accessible to confu app. Even the exported types. It does not read the module, therefore it cannot access any of the types. If I go back and introduce the read edge again, that allows code in confu app to read the public types in the exported packages. In tomorrow's Under the Hood talk, we'll go through a lot more of the details about what this means and how this notion of public changes with modules. But the main thing to take from what I've just gone through here, aside from understanding what readability and exports and what this means for encapsulation, is public no longer means accessible. This is a really fundamental change to the platform. For the last 20 years, all public types have been accessible. Now we're introducing modules, we're introducing encapsulation, public types. Some public types may no longer be accessible. So this is a really, really fundamental change. And when I say not accessible, I'm talking about at compile time, and I'm talking about at runtime. And at runtime, I'm talking about static references, I'm talking about core reflection, I'm talking about method handles. They're just not accessible. So that's the concepts out of the way. We'll now move on and start talking a little bit about the platform modules and get into some of the changes to the command line tools and how we will compile and run with modules. So the first thing I want to get into is the platform modules. Mark showed a spaghetti diagram in the keynote this morning. You may have seen other spaghetti diagrams that Mark has shown over the last couple of years. Moving the core platform to modules has been an enormous effort, multi-year effort. Mostly we'll be trying to sort out some of these dependencies between various parts of the libraries that have built up over the years, and this has taken a long time to do. So we've been able to, over a number of years, is get to the point where that big tangle diagram that he showed in the keynote this morning gets to a reasonably clean module graph. This one is particularly clean because it's actually the transitive reduction. So you're not seeing all the edges there, but it is nice and clean. The important thing about this, and this will come up in the presentations tomorrow, there are no cycles, there are no split packages. This is a relatively clean module graph. Things to point out is right down at the bottom you see Java base. That does not depend on any other module. That is the one module that's known to the language, known to the VM, and known to the module system. All the rest of the modules you see there will all depend on Java base. One other thing to say is this module graph here is the standard module graph. When I say standard, I'm talking about the Java SE modules. So all of the modules in this, at least that are in orange here, all start with java.star. So in JEP 200, there's a proposal for how we name modules, and all of the standard modules, meaning those defined in the JCP, has been proposed to start with java.star. That's irrespective of what the package name might be. So there may be some APIs that are javax.star packages. The module names have been proposed to be java.star. So these are the standard modules. There are, in addition to this, a corresponding set of JDK modules. These are JDK-specific modules. And I'll show you the full list that we have in the current prototype and the current builds with java-list mods. So the launcher has been extensively updated in the Jigsaw builds with a whole bunch of new options. One of them is list mods, and in this particular usage here, you can just think of it as listing all of the modules that are in the runtime. So when I download a Jigsaw build, the JDK build, and I do a Java list mods, it lists me all the modules that make up that runtime. All the java.star modules that you see there, they are the standard modules. You look down through the list, you'll recognize some of these: Java base, Java logging, Java naming. Java naming is JNDI. Some of these you won't recognize, maybe because just there isn't a good name to give some of these huge modules like Java desktop, which is where you find all of the AWT Swing APIs. They are what are exported by that module. The JDK.star modules are the JDK-specific modules. Some of these modules do not export anything. They are just tools. Some of them are service providers. We're not doing any talks on services in the 4 sessions we have, but some of these modules are purely service provider modules. There's some JDK-specific APIs in there. In the talk this morning, earlier today, I tried to explain the difference between the standard APIs and the JDK-specific APIs. So there's some supported and documented ComSun and JDK.star APIs. These are the APIs that are exported by a number of these JDK.star modules. So this is the full list if you try it out, and there's various other sub-options on list mods that you can get more detail on the modules. Now I want to move on and start talking a bit about compilation of modules. And I'll start right down at the bottom in our module graph with the confu-baz module, because that was a library module in the module graph we had a few minutes ago. So this is a Java C command. There's no new fancy options on this Java C command. -d is the directory where the compiler outputs to. That's the destination directory. I'm giving it a bunch of source files to compile, and just like any compiler, it goes from java.java source to class files. The way this code is organized for this example is the directory structure is src, module name, and then the source files. That is how it's organized here. So I'm compiling all of the .java files that are in the confu-baz directory tree, and I'm compiling them to .class file. The important thing to take from this is the module declaration, which was in moduleinfo.java, is compiled by the compiler along with the rest of the source code, and is compiled to .class files. To build up the next few examples and show additional compilations, I needed to introduce one other concept, and that is the module path. And the module path, you can think of it as the module equivalent of the class path. With a class path, you're giving it usually you're giving it a sequence of sequence of jar files. With the module path, you're always giving it a sequence of directories. And in each of those directories are modules. Those modules may be exploded on the file system, like for the previous compilation where I went from source to .class files, or they may be packaged modules. I will go through packaging of modules in a few slides' time. The way modules are located, and it's important to understand how modules are located for both compilation and runtime, is that if you want to locate a module named confu bar, then we will look for that module in dir 1. If it's not in dir 1, it'll try it in dir 2. If it finds it there, then it'll no longer look for any more in directory 3 and so on. A module can only be in one place. If it's in any subsequent directories, it'll just be ignored. It's not possible to have two versions of a module in a directory. It's an error to have two versions of confu bar that are in directory 1. Module system said, I can't deal with this. There's two of them there. How do you know which one? So that eliminates some of the complexity with that you would otherwise have, the unpredictability that you would have. So what happens at both compile time and at runtime is when you're searching for a module and you're trying to resolve its dependencies, we're going to be using a module path so that the compiler or the runtime will be able to locate the modules. So here's the next Java C command. So I've moved up a level. We assume we've compiled our confu baz as we did in the previous example. Now I'm going to do a compilation with a module path. I'm going to compile confu bar. Remember, it has a dependency on other modules. Where is it going to find those modules? It's going to find them on the module path. So this is like doing a Java C-CP with the class path, except that modules now are found on the module path with the dashed module path option. That's compilation. I want to show running next. Now, the command I'm going to use for executing my application will initially look a little bit complicated. We'll simplify it over a couple of slides. But this is the command I'm using here. Java-module path, I'm giving it the module path, -m for the main or initial module, and then I'm telling it what the main or initial module is and what the main class is. What happens here is that it'll try to load module confu app. It'll resolve its dependencies. We'll go through that in the next couple of slides, and then it'll run its main class. This initially looks a little bit cumbersome because I'm giving it two pieces of information rather than just the main class as I would have done before. We'll get to that in a couple of minutes. The important thing to take from this is Java Launcher also has a module path option, and we've tried to keep the Java C and Java Launcher options to work the same way, so that it's the familiar feel that Java has always had. So let's go and see what happens when we try to run the confu app module. So going back to our module graph that we had earlier on, confu app has a dependency on 3 modules. Therefore, those 3 modules will need to be located. Confu bar, which we would hope is on the module path, Java base, and Java SQL. They may not be on the module path I've specified with the -module path option. They should be found in the runtime image, something we call the system module path. So the important thing to understand is that running with Java-M will trigger resolution. It'll trigger generating that module graph. It's a very, very simple module graph in this case, and this is very, very simple resolution. It's not complicated set solving or anything like that. It's simply finding the dependencies and essentially building up that module graph that we had in one of the early slides. So we've got all of these modules that will be located at startup. If any of those modules are missing, then of course startup will fail. Module missing. Mark showed an example of that earlier on in the keynote. And one of the diagnosability options that we have, or diagnostic options that we have on the Java launcher, is there's an existing xdiag option has been there on the Java launcher for many years. There's a new sub option in the jigsaw builds to be able to see a little bit more what's going on. So this will actually trace what happens at startup, so you can actually see it. Where does it locate the modules, and how is it building up the module graph? I've really cut down the trace output here in order to fit it into the slide. But the important thing is when you're trying to locate modules and then their dependencies and building a readability graph, things can go wrong. You might get exceptions. So it's important to be able to know where the modules are being located. So this is an option that helps to debug any problems that might happen during startup when dependencies are being found. So that's compilation, that's running in one simple way. And I want to move on and talk a little bit about packaging. Mark touched on modular jars in the keynote this morning, so I want to spend a couple of minutes on modular jars. A modular jar is just a regular jar file, except it has a module info.class in the top level directory of the jar file. So in this example, I have compiled everything that is in module confu app, packaging everything that is in confu app. I'm going to package it up with the jar tool to create app.jar. So if I was to look inside of app.jar, I see the module info.class, that's my compiled module declaration, and I see all of the other class files for the application. The jar tool has been extensively revised and updated with a bunch of new options to support modules in the Jigsaw build. I'm using this here. And so this jar command may not initially look familiar, but it's because the jar tool now supports GNU style rather than Unix. It also supports Unix style options to create the jar file. An important thing with this command here is I'm setting the main class of the module when I'm creating and packaging the module. There's other metadata that I can add to a module when I'm packaging it. So there's a clear distinction in this module system between what is in the module declaration, what the language, what the VM, what the platform knows about, and then all of this other metadata that may be added at packaging time. And the main class is one of these things that can be added at packaging time with the jar tool. So this creates app.jar. So important properties about modular jars is it's part of the interoperability and migration story for modules. We'll get into a lot more about migration tomorrow, but an important thing about modular jars is a library can be a jar file that works on the class path, or it can be a module that works on the module path as a module. So it means that you can compile something for an old version of the platform, javac-release, if you haven't seen that new option on javac, compile it for an old platform, add the module descriptor, and that allows me to use it on the class path with JDK 8 and older. I can then I use the library as a module with JDK 9. So that's really, really useful, particularly for important libraries that can't move completely to modules in one release because they want to be able to support users on previous releases. So being able to have one jar file that can be on either the class path or the module path is a really, really important property. So I mentioned about the jar tool being updated. Here's another option to be able to print the module descriptor and see what's in a jar file. -p in this in this slide here is short for the GNU version of --print module descriptor. It's just a shorter form of it. So being able to look at a jar file and being able to see what module is in that jar file, what does it depend on, and then what's its main class and other version in details, all of this can be printed out by the jar tool. So this is quite useful. So now let's go back to our launch command and our Java command and see how it works when we've packaged our module as a modular jar. It becomes a little bit simpler. Java-M is specifying just the module name. I'm no longer needing to specify the main class. This is a bit like Java-jar, except we're dealing with modules now. This is a packaged module. It has a main class. The module system is able to load that module and invoke its main class, which is good. The module path in this example has two directories. The packaged modules are in mlib, and I have left some of the dependencies as exploded modules in the mods directory. just for this example to show how a module path can have multiple directories. So I just want to say a bit more about modular jars and class being on the class path as regular jar files or being modules on the module path by just showing some of the command line options that it might look like. So here I have, let us assume that we have our BAS and our app as modular jars. I'm going to put them on the class path and run them with 9, run them with 8, maybe whatever they're compiled to. And these libraries, even though they have a module.info, module.info.class in the jar files, they will still work as libraries on the class path. The module.info.class name is not valid as a valid class name, so it will be ignored by the previous releases. So that is how this actually works. We run them on the module path, so assume everything is packaged as modular jars in their yamlib directory. My same library can be used on the module path. So I've used it on the class path, I've used it on the module path. Now we get into something a little bit more complicated. I can mix the class path and the module path. Suppose, for this example, we will have confu.baz as a module on the module path and everything else on the class path. My main application, my main class is in the jar file on the class path here. It is not on the module path. How do we know that, how does the launcher know that, oh, here is a module path and in there I can find 2,000 modules, which of those modules should be resolved? Java Launcher doesn't know that, the module system doesn't know that, so this command has an add mods option to the launcher to say, I want to use this module on this module path. So when you're mixing modules and class path, there will be cases where you have to tell the system which modules you want resolved. This is because we're mixing class path and module path together. We'll have some more examples of that tomorrow. But the important thing is that being able to have modular jars, we're not going to force everyone to move to modules in one go. And in fact, a lot of tomorrow's talk is about this very topic. So one final thing that I want to spend time on is linking. Mark mentioned about the linker in the keynote this morning. In the Java ecosystem, we've always had compile, run, or compile, package, and run. This will be the first time where we introduce an optional link phase and a linker tool that will allow modules to be linked together to create a running application. So it's akin to the native linker, and the way it works in the current builds is, and I'll show an example of this in a minute, but at a high level, we can, like Java-C, like Java, we will give the linker the module path where to find modules, what modules that you would like to include. Those modules, their dependencies, their transitive dependencies will be linked together to produce a runtime image. So JEP 220 defines the layout of the runtime, the modular runtime image, and we've already moved JDK 9 to that layout for just over a year ago. And the linker tool will allow you to create any custom runtime image that is your application or specific libraries and their dependencies. So these will be just the minimal dependencies that are needed to run that application. I'll show a command on the next slide, but the way that runtime image is laid out is there's a bin directory where you have the launchers, and there's a conf directory where there's configuration for that runtime. I talked a little bit about this in the talk earlier on, but as part of cleaning up the runtime image and essentially blurring the historical distinction between what we know as the JRE and the JDK is, we've cleaned up and located all of the configuration files like security security files and anything else that is meaningful to configure the runtime have all been moved into the one location. So there's no confusion over what can be changed in order to customize the runtime. It's all in the one place. So they're the two important directories in there. Classes and resources associated with the modules, they're all stored in a completely new format. No longer jars. There's no longer any jar files in the runtime image. It's a new format that's optimized, or enables a whole slew of optimizations that we want to work on, and for things like startup, for footprint, for sharing, and so on. So I'll show the linker tool in one simple command first. And I'm going to create, with the linker tool, a minimal runtime image that contains one and only one module, Java base. This is the minimum module the minimum runtime that you can create. So like Java and Java-C, you give to the linker tool, and the linker tool is called JLink. You give it a module path where to find the modules. I'm using the add mods to tell it what modules to add into the runtime image, and then I'm giving it the output directory where it's going to create it. This is a simple JLink command. The JDK JMods assume that's an environment variable where you find the package platform modules. I'm going to use the list mods option like I did on the Java launcher in one of the first slides. You might remember I did a Java list mods in one of the early slides where we listed out the 60 or 70 modules that are in the regular JDK builds. This runtime image that I've created with this JLink command is one module and one module only. Like all linkers, there's a whole slew of complicated options to do fancy things. This is the simplest option. This is the simplest command you can get. But if you try out the Jigsaw builds, you'll see some of the options in there and how you do compression, how you do stripping, and a whole bunch of other complicated things that you might want to do. So this is the simplest one to get you down to a minimal runtime. I'm now going to do the similar command, but I'm going to take the Confu app application that I had in the early slides. So remember, Confu app had a dependency on Confu bar, which had a further dependency on Confu baz, and so on. And there were 4 platform modules that were in that module graph that I showed in the early slides. So I'm asking the linker to create a runtime image with just one module. It ends up linking in a total of 7 modules because that is the transitive closure. There's 7 modules that need to be brought together and linked to represent that module graph. So this is quite useful, and as I said, there's a whole bunch of other interesting options that you can use with the linker, and but not for this session. This session was really about basic concepts. So I want and some basic command lines for compiling, running, packaging, and now linking. So that's all I wanted to cover in the introduction, and we're going to use the rest of the time for questions. And I think Mark is going to come up for questions. As I said, tomorrow we're going to have the advanced talk. So this builds on the concepts that we've actually talked about in this session, and we spend time on migration. So in room first thing in the morning, I think we're in here for 9:30, and then under the hood session, which will cover the science behind modules. We're going to present that tomorrow evening at 5:50 in room 5. Some more information. Everything that we're working on here is all the documents and all the material related to that can be found on the OpenJDK project Jigsaw page. That has the links to the JEPs and other documents that we have. The mailing list that we ask people to send back. Feedback and questions is the Jigsaw Dev OpenJDK JavaNet list. And then the early access bills, the link is at the bottom of the slide. So if we have questions, we have a quarter of an hour left. So if we've got questions, so
raise your hand, please. If you're near a microphone, use it. Otherwise, I'll bring it to you. You can also use Twitter. If you tweet at the hash Jigsaw tag, then I'll look periodically, and we can pick up questions that way as well.
So the way the questions are going to work is Mark's going to get a bit of exercise running around with the microphone.
I'm doing the Stefan Janssen-inspired weight loss plan.
So, regarding the accessibility check, is it enforced by the JVM in bytecode, or is there a runtime enforcement for those?
Oh, this is runtime enforcements. So this is both in the VM, it's also in core reflection and method handles.
Yeah, but it's not in bytecode, so the JVM itself doesn't care. If I have some other bytecode generated by another programming language or anything.
This is all enforced by the VM. It doesn't matter who generates the bytecode, whether you're spinning the class files dynamically or they're generated by the compiler. Access checks are always done by the VM.
It's enforced for all bytecodes,
Yes.
not just some bytecodes.
Sorry, Mark. Oh.
Yeah, I had a question about the module resolution. You have the module path and the system module path. Which one, is there an order in which it is resolved, or can I put a java.sql module in my own classes and have that executed instead or linked instead of the Java SQL from the JDK packages?
Okay, so there is something I didn't talk about today, which is the system module path, which is where all the platform modules live. So you could conceptually think of that as appearing before your application module path that you specify with java-module path. So that's why Java SQL will always be found before java.sql.jar that you might put in some directory. But one other thing that I didn't talk about today is there are some limited cases where you do need to replace or upgrade the system modules. App servers typically have to do it, and there is a mechanism for that too.
Here's a question on Twitter. How do modules handle circular dependencies? They don't. No circularity in a module graph. It's just verboten. So, circular dependence in a module graph is a sign of a bug.
Right, and resolution would fail if it finds a circular dependency.
Mm-hmm. Hello. Suppose you have some common code which you're going to use, for instance, somewhere inside JDK, but you want to keep this common code private from interface perspective. Is there any possibility to do such trick with your model system?
Do you want to talk about qualified exports, or do you want to leave it till tomorrow? So yes, there is a mechanism in the module system for if you're creating a group of modules and you've got some common code that is exported, you can export it to just your friends, just the modules, and so there is that mechanism. It's called qualified exports. We'll touch on it in tomorrow's presentation.
Can you please go back to slide 37?
The linking one?
Yes, if you look at the list of the modules, you see the add 9.0 behind the JDK modules.
Yes.
The add 9.0 is not part of the name of the module, right?
Okay, the way the list, so.
Because I don't see the add behind the custom modules.
Right. So in this example, these three Confu modules, when I packaged them, I didn't give a version string. The platform modules do have a version string for informational purposes. This will show up in the list mods. It'll also show up in things like stack traces and some exceptions as well for informational purposes.
You can also add versions to your own classes or your own modules.
Yes.
Okay.
So there's a timely Twitter question on this topic related to this. Is versioning supported by the new module architecture? Can one module depend on version 1.1 of logging and another module dependent on version 1.4 of logging? Versioning is something that we've decided after some painful experience not to do, which might seem wrong. It's a model system. Of course, it should do versioning. You should have version constraints and version strings and numbers and all of this other stuff. And we did that in the first Jigsaw prototype, and it turned out to get really, really complicated. So we decided not to do it. Part of the observation we made was, well, if you look at how this stuff is going to be used, we already have tools like Maven and Gradle and Ivy that handle dependency management and just tackle the really hard problem of versioning. If we tried to do that in the module system as well, we might always not get the same answer. We might do it differently. You know, in 5 years, some super amazing, new build tool might come along that does a better job. It just didn't seem right for the module system to be in the version selection business. So versions in the module system they're sort of in a way an optional part of the module name. You can specify a version when you package a module. It can be something that your build system provides. Usually it's the build system that knows, rather than your source code, which is another reason to keep the version numbers out of the source code. And version strings will show up as in diagnostic messages and things like list mods output. But in general, we're taking the stance that it's up to build tools to arrange modules on the module path in such a way that the right things will be found by the module system. The module system will take the first module of a given name that it finds. It will refuse to deal with any duplicates and just give you the advice that you should go fix your build system. Okay, sorry, there have been a couple of people here who had their hands up for a while.
Yeah, I'm assuming that the result of the linker is platform dependent. So in that case, is there like a cross-compilation? Because if you have a Raspberry Pi, you don't want to launch a linker on your Raspberry Pi, you want to do it on your PC.
Right, so the linker can link to other targets, yes. So you could be on Linux x86 and target Linux ARM. What you need to make sure is that your module path has the modules for Linux ARM rather than Linux x86. So that's something that's not quite yet enforced in the current prototype, but eventually it has to be, so that you don't mistakenly end up linking some, I don't know, Linux PowerPC and Linux x86 and then try and run it and link it on Linux ARM. So yes, so there is that ability.
Since you already addressed one of the questions that I had regarding versioning, I have a follow-up question. Assuming that your module uses two different modules that in turn use different versions of another module, how does this solve the conflict? It doesn't. So
if today you have a bunch of jar files on the class path and you have two different versions of some artifact, you're already in a very bad situation. Right, no module system will help you. Every module system will insist that you resolve that conflict in some manner, if only to avoid the inevitable class cast exceptions that you'll get when things meet up. Now, for really sophisticated applications like an app server or something like that needs to spin up things dynamically, there are ways for a sophisticated application to spin up what we call another layer of modules in a way that allows multiple versions of some module to exist. But we try very hard to keep those things from ever meeting because it just leads to very difficult to diagnose errors.
Yeah, I had a specific scenario in mind where, I mean, the error did only show up when running the application. It was an OSGI module that ended up having references to two different versions of some CXF jar.
And how did this work out for you?
Well, it crashed, but I mean, I was hoping that the crash should be caught at compile time rather than at runtime.
Well, certainly, if you're compiling a bunch of those modules with Jigsaw, you will get the error at compile time. You won't have to wait until runtime. So it's maybe helpful in that regard. How much time do we have left?
You got 7 minutes. There's a bunch of hands on the left. So you're right.
Hands on the left, hands on the right.
I have a question regarding the naming policy of the JDK modules. So I noted that there is a java.sql and java.sql row set. So does it mean that the row set is the submodule of the java.sql module? Okay, and if my functional module requires the java.sql.row set, that means that all the export part of java.sql will be also available for my functional module.
Okay, so there is no notion of submodules. The reason for the split between Java SQL and Java SQL row set is so that we have a small Java SQL module that can be used on embedded system without bringing in all of the dependencies that the row set API and the footprint that the row set API would bring. In terms of the naming, then the convention that is used is, where possible, the dominant or the topmost package name of the API goes into the module name where it makes sense. There's a couple of modules where it doesn't make sense, like Java Base, because if I was to explode Java Base and look at all the exported APIs, they're Java IO, Java Lang, Java Net, and so on. There isn't an obvious name there, and that's why it's called Java Base. So there's a handful of modules where that convention doesn't apply, but for the most part, it's the dominant package name goes into the module name in what we have currently on the table.
Yeah, one more observation about the row set. The row set module depends on the SQL module. So if you use row set, you'll have to have the SQL module around. But to Alan's point, you can use the SQL module without row set. Does the row set module require public SQL? I think it does.
I think it does, yes.
It probably does. But that's easy to check. Let's see, fair time to Twitter here. What if the same class exists in multiple modules? Well, then you better hope they don't talk to each other. If they do, the module system will refuse to configure that.
Right.
All right.
So what is your advice then to companies that build fairly large software projects and today use OSGI? Is the advice then stick with OSGI? Because, for example, supporting multiple versions is quite critical and quite commonly used. So I'm a bit surprised about the statements on we're not supporting versioning, and if you have multiple versions, you're doing something wrong. So what's the advice for larger existing software projects that use OSGI?
Well, let me add a little nuance to my statement. If you have, what I meant was, if you have multiple versions on the class path, you're doing something wrong. If you're in a dynamic system and you have to have multiple versions, there is a way to do it with Jigsaw. It's not the easy path because it's not the most important thing to support, but it's there and it can be done. As for advice about OSGI, well, if it's solving your problems, then keep using it. And there are plenty of facilities in OSGI that will never be in the Java Platform module system. This module system is not meant as a replacement for OSGI, especially if you're using the dynamic lifecycle facilities and its more complex, fancier service mechanism, and some applications have legitimate needs for that. So, this is a question. I basically don't have any advice. Just look at what your needs are. If you've built an application and you're using OSGI really only for the module facilities, then you could evaluate, is it worth moving to something that's simpler? And the answer to that question is up to you.
So in the opening, you show us the wiki page for the jar hell. Do you think it will be a wiki page for the modules hell?
Who knows? There might be, just because it's on Wikipedia doesn't mean it's true. And yeah, there are some people who just don't like this approach, and well, that. Can there be module hell? Well, if there is, hopefully it's a higher rung of hell than than jar hell. Maybe several higher rungs. In complex software systems, the modules are a tool to bring a bit more sanity. Do they make it easy to write large complex software systems? Well, they make it easier, but no, I don't think anything can make it easy. Is there somebody else around here?
There are some frameworks who have multiple implementations who can be implemented by anyone and then defines in a configuration file. How will this work with this system, as you won't require all the implementations?
That's a pretty advanced, it's a reasonably advanced topic, and the margin of the page does not allow me to fit an answer here. But I encourage you to come to the advanced and the under the hood talks And you'll see more of the mechanisms that allow that sort of thing to be handled.
There's a couple of hands on this side.
1 minute, 30
1.5
seconds.
minutes.
The sign has turned red. Where were you?
What happens if two modules you depend on export the same package? Will you get a warning, at least an error?
Never happens. That will be an error at resolution time. Both compile time and run time before anything happens. The resolver runs. If it finds a conflict like that, it gives you an error message. Hopefully the error message is helpful and you can go fix the problem.
And it's much better to get that error at configuration time and
So
start.
split packages like that are just evil.
Hi. You can link a runtime together, I understand. Will it be possible to link a WAR file together?
I referred you to the specification lead for Java EE9. I have no idea. It's certainly our intent that there be an EE, the modules be adopted by the relevant EE standards in the long term, but that's a long-term thing. You know, we do talk to a bunch of the EE spec leads on a regular basis. You're talking about WAR files. Sorry, if you're talking about WAR. Sorry, you are talking. I'm sorry. If you're talking about WAR files, you are talking about Java EE. If you're talking about WAR files, you're not talking about. Okay, I'm sorry. I can't parse your question. Next question.
All right, the
We're
time
out of
is
time.
up.
Oh,
so
the screen's
we-
turned
right, yeah, so
turned black. We're finished. Okay.
Catch
Thanks
us
very much.
outside because I presume there's another session in here.